All right. So yeah, welcome to our meeting for this week. And then if you remember from that Facebook post that Russ sent out, unfortunately, there's not going to be any meetings or anything next week. So yeah, that's just canceled next week. We'll pick them back up 2 weeks from now. But yeah, just keep that in mind. Today we're going to be talking about the Naïve Bayes classifier, which is another machine learning algorithm that we're going to learn about. This one we should be able to complete just in one meeting, hopefully. Like, Kaushik, is this your slide? Or
Sure, I can go for it. Yeah, we're just going over the Naïve Bayes classifier. So to kind of give some background on that, we're going to go over Bayes' theorem, something for probability. Then we're going to go over the model itself, and then go over some example code for that.
Yeah, so let's just get started. So if you haven't heard of Bayes' theorem before, this is what it is. And so essentially what this notation means is it's basically, oh, whoops, not. Basically, what we're talking about probabilities here. And this is what the Naïve Bayes model is basically based on, right? It's based on probabilities, right? So when you write, you see P of A and then this line B, P of B. So what this means is, so let me make this bigger. P of A, all right, what this is saying is probability of A, right? And then A can be whatever, it could be, an attribute or an event or anything that has a probability, right? And so, probability of B is, as you might infer, it's just probability of B. And so then we have this one last notation here, which is probability of B, and then this bar A. So what does this mean? Well, this actually denotes our probability of B given A. So what does that mean? Well, this is the probability that B is true only in the case that A is true, right? So probability of B given A, right? So this is the probability of B, assuming that A is true, given the case that A is true. And so if we look into this formula now, we can see this is, we can use this formula to find this specific probability, right? Probability of A given B or the posterior. Okay, and so this, it's just first you start with P, the probability of B given A times the probability of A, all divided by the probability of B, right? And this is essentially like the magic formula that you need to know. But this may seem counterintuitive at first, right? This is just like, a bunch of different probabilities. Why does this work? Why does this make any sense? Well, the way that at least personally to me, that makes it intuitive is if I draw it with trees. All right, so I'm going to draw a tree here. And so first I'm going to start with A, right? And the two branches coming off of it are going to represent the probability of A. So this is probability of A. And this is, the opposite probability, right? Probability of not A. Right, so if the probability of A is like 70%, right, you write 0.7, then the probability of not A would be, the 1 minus probability of A, right? But this part isn't too important, right? What we want to focus on is this section, right? So we have a 0.7, 70% chance of A, right? That's the probability of A. So the chance that we go down this path, that this case occurs, is 70%. So now we consider the probability of B. And we can draw the same paths forking off of that. So this would be the probability of B. But there's a caveat. Caveat? I don't know. There's a condition here, right? Because this isn't just the probability of B. Remember that this is the case where A has already occurred, right? The 70% of the time, 0.7 of the cases. This is, this is given that A has already occurred. So this is actually the probability of B, right? B being true, given that A is true. So we know this to be probability of B given A. And we can write this to be like 0.6 or something. And then here, we have the same thing, the opposite, where we have probability of not B given A. And again, that's just 1 minus the other, so 0.4. Right, and we can define the same things here. So, if we have another thing here for B, we have probability of B given not A. And again, probability of not B, not A, right? Probability of not B given not A. Right? So we have all these probabilities. And now let's look at what the final case is for all four of these, or let's look at all four of these final cases. So given the probability of A, if A is true, and then B is also true, then for this case, we have that A and B are true. Right, so I'm gonna write sort of like I guess an A, B, true table here, right? So this column represents A's value, this column represents B's value, right? So this would be true and true, right? Because both of them are true. Now if we go down here, go up this path, follow it down here, we have A is true and B is false. So true, false. And then we can follow the same logic down here, right? A is false, B is true, and then both are false. And one thing to notice here is that we can actually calculate the probability of these final cases. Right? So how do we calculate the probability that A and B are both true, given this table? Well, we know that 0.7 of the cases are, in 0.7 of the cases, A is true, right? And given that A is true, we know that 0.6 of those 0.7 of all the cases also have B as true. So it's just a simple multiplication here to find the probability, right? Because, like I said earlier, this is 0.7 of the cases where A is true, and given these 0.7 cases, 0.6 of the 0.7 cases, B is also true. So we end up with 0.42 as our final probability for A and B. And so, we could calculate the same things here and here, but this top one is the important one. So now, the next step is to draw another tree. And the thing to notice here is that we can actually start from a different, we can start from B instead. So we go to B, right? This is the probability of B. And then we have, the same cases. Right, probability of A given B, blah, 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 blah. Right? And then again, we end up with the cases where if we continue along this this column labeling, right, where A is the first, B is the second, we get true, true. This would be false, true, true, false, false, false. Right, and again, this top part is the important, this top path is the important one. Because again, we can calculate the probability of A and B. So this would be like and B, right? The probability of A and B both being true as probability of B, and then times the probability of A given B, right? Given that the probability of B is true. And this is just another way to be able to calculate, that both A and B are true. So we can say that probability of B times the probability of A given B is equal to probability of A and B. But if you remember, we also had this other equation up here for calculating the same thing, right? Where we follow the path, probability of A times the probability of B given A. So we write that down too, since they're both equal. Probability of A times the probability of B given A. Right? And then from here on out, it's just a simple algebraic manipulation to be able to derive the final formula, which is here. Right, so if we want to find probability of A given B, we just divide both sides by the probability of B, and we get probability of B given A, just rearranging these two, times the probability of A divided by the probability of B. Right, and so this is why this works mathematically. And so yeah, this is what the Bayes, naive Bayes algorithm is based on. And one important thing to note here is that the reason it's called naive Bayes is because it makes a naive assumption that every single feature that you input into the naive Bayes algorithm is independent and of equal weight. All right, I'm going to repeat that again. This naive Bayes assumes that they're independent and of equal weight. And so obviously you can see why this this can be considered naive, because in real life, when you have especially when you have more and more features, it becomes more and more likely that some of them are in some way correlated or related to each other, right? And naive Bayes doesn't account for that. And so but regardless of that, there's still use cases and scenarios where using naive Bayes can still prove to be a pretty effective technique compared to other machine learning models. Right. So now that we know the Bayes theorem, now we can generalize it. Right. So how do we use Bayes theorem? How do we use Bayes theorem as a classifier? Well, let's see. Let me make this bigger. Right. Well, the way that we do that is that we apply it to different classes. So let me remove all this. So what we want to do in the case of not using naive Bayes as a classifier is given y, in which well, actually given, okay, so now instead of using A and B, we're going to use X and Y, right? And so now we're going to want to use lowercase y, capital X, right? And this is what we want to find, where y is equal to a, actually let me write this down, make this bigger also. Where y is a class variable and X is a feature vector. And so in practice, let's go with an example with, say you're trying to, let me think of an example. Say you're trying to predict whether or not it's a good day to go play golf, right? And in your data set, you include, so, your data set, you include something about outlook, which would be like, for this, let's define 3 class variables. Should be rainy, overcast, and sunny. For temperature, you could just put hot, cold, and mild. And then, et cetera, et cetera. We can continue with like humidity, wind speed, day of the week, stuff like that, right? And so what a class variable is so this would be whether or not we play golf, right? Or if it's a good day to play golf or not. right? So this sample would be like yes, no, no, yes, blah, blah, right? And for our particular example, we have two class variables, possible class variables as output, yes and no. And what Naïve Bayes does is that it calculates the probability of an input vector being any one of these classes. And x is our input vector, the feature vector. So essentially what we're saying is if we were to run it on like a specific set, say it was like cold, rainy, humidity is high, wind speed is also high, right? So given this feature vector, right, of all this particular inputs, now we try to give probabilities for every single class variable. So now our first one would be yes, right? So play golf, yes. Let's say our model gives a probability of 12%, right? There's a 12% chance that it is a good day to go golfing today. And then for no, we get another probability. Our model says that it's 88% likely that it's not a good day to go golfing, right? And with more classes, we just we have more predictions, right? So now this could be like 58, right? And then this would be like maybe, right? But we're just gonna assume 2 for now. So this could, it says maybe 30%, right? And the output of our naive Bayes classification is just the highest probability, right? What our model thinks has the highest chance of being the correct label for our features, right? In this case, it thinks, based on the fact that it's cold, rainy, high humidity, high wind, I think that it's most likely that it's not a good day to go golfing, right? And so we calculate these probabilities for every single class variable. And so if we were to plug this into here, it would be, P of the probability of yes given, this big vector, right? Blah, 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 that is windy, cold, humid, whatever, right? Our probability of yes, it is a good day to go golfing is low. And then, we can say the same thing about the other probability, right? We calculate, the probability of no is high. And so now the question remains, how do we actually calculate these probabilities? Well, this is where the naive Bayes theorem comes into effect, right? And so when we're trying to solve for a particular class variable given our input feature vector, we just use the naive Bayes theorem to be able to calculate it. So probability of y given x is equal to the probability of x given y times the probability of y, all divided by the probability of x. Okay? And so now, this is essentially what we do to calculate every single possible class variable, right? But we have a problem though, because remember, the probability of y given x is actually a vector, right? It's not just one value. It's 5, it's 10, it's n amount of features that you have inside of your data set, right? Whatever you're training it on. So how would you be able to find the probability of a specific vector, right, if it's not in the data set, right? So say like, again, this is our specific vector, right? That is cold, rainy, high humidity, high wind, right? So if there are no specific samples in your data set which have this exact feature vector, then you won't know what the actual final probability is, right? Because you never see it in your actual data set. And so this is where the naive of the naive Bayes comes in, right? So we're just gonna remember that x, wait, let me make this a little bigger, sorry. Remember that x is a vector, And so we're just going to define x as this big vector of x1, x2, dot, 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 xn, right? For however many vectors there are, or for however many features there are, sorry. Right? And so this is actually the probability of y given x1, x2, x3, blah, blah, blah. And so what we do here to be able to resolve this issue is that we actually split up the probability. So we assume that the probability of, so here what we're trying to figure out is this, right? Probability of x given y. So probability of x given y, right, which is equal to probability of, for here, let's just say there's only two features, okay? So x1, x2, right, given y. So if we're trying to figure out the probability of both of these combined given y, what we're going to do is we're going to split it up. So we're going to say that this is actually equal to probability of x1 given y times the probability of x2 given y. And the reason we can do this is because we make the assumption that all of the features are independent. And you know, this is where that, again, where that naiveness comes from, where that error can occur, right? Where when we assume that we can just split it up in this manner, right? But yeah, so this is how it works. So then yeah, there's also this one more notation that you have to learn, but it's not too difficult. So it's called pi notation. So if you remember from last time, or I think from 2 meetings ago, the summation notation is a sigma, right? Where if you have like n equals 1 to like 5, right? Of say n, right? This would be equal to saying n equals 1 of n, so 1, and then add it to the next one, so n equals 2. So it's like a for loop in math, right? N equals 3, n equals 4, right? And then again, if I specify n squared, this would be the first one squared plus the next loop squared, etc. Right? So now we're going to introduce the pi notation, which is a capital pi. And what the pi notation is instead of performing the operation on each value of n from the starting to the ending integer, and then adding them all up, we perform the operation on every single n from the start to the end integer, and then we multiply them all together. So if we were to do the same thing here of n squared, we would get that 1 squared times 2 squared times 3 squared, blah, blah, blah. And so this is what the pi notation is. And this is actually pretty useful for Naïve Bayes in particular, because we can actually express it in terms of pi notation. So so remember, what we're trying to do here is we're trying to split up this Bayes theorem formula that uses a vector, right? We're trying to split it up. So what we can say here is that py given the vector x is equal to, and then we can just split it up by multiplication, right? P of x1 of given y, p of x2 given y, dot, 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 right? And then times p of y. Right? And then we can do the same thing on the bottom, right? P of x1 given y, p of x2, blah, blah, blah. So if we're just going to split it up like this and multiply each term, we can actually express this in terms of with a pi notation symbol. So since we're multiplying each value, we actually say. And then one last thing is that we need to take this P of y, the probability of y, out in front because it's not part of the, this infinite, or not this infinite, but this multiplication of all the elements of a vector. Right, so P of y times the multiplication of from I equals 1 all the way to n, where n is the length of your feature vector x, of p, the probability of xi given y. All right, and then again, the same thing on the bottom. And so you can see how this is the same thing, because when you unroll this, when you expand it out, you get p of x1 get probability of x1 given y times the probability of x2 given y, all the way up until probability of xn given y, right? It's the same thing that we had up here. Right, and so so this is how you calculate the final probability of of a particular class. And so how do you find the probability of how do you find all these values first? Well, one thing that we can actually do is we can do a simplification of our equation here. Yeah, you're right. On the bottom, it shouldn't be given y. It should just be probability of x1, probability of x2. That's correct. Yeah, that's my bad. Yeah, so here we have the probability of all the vectors, and so you essentially just take the probability. You take a vector x, you take the probability of every single one of its elements, and then you multiply them all together. Is what we're doing on the bottom. However, the simplification that we can make here is that remember that we're doing this equation, right? This calculation for every single one of our possible output classes. Right, so here, we're testing whether or not it's a good day to go golfing. That'd be yes or no, right? Two possible classes. So we do this for, would this be yes, and then we do it again where y is no. But what you see here is that this probability of x given y, that is dependent on y. Probability of y, that is also dependent on y. But probability of x is not, right? And so the probability of y given x, right? We're only changing the y here, right? We're only testing it on different possible output classes. We're not changing what our input features are, right? Because we're looking at all the possible probabilities for one specific input, right? For this particular one. If we wanted to change it, then we move on to a different one, right? We choose a different input feature vector. But during our calculations, this doesn't change. And so what this means is that this value is actually a constant for every single y, right? No matter what y you put, like whether you decide to calculate for yes or whether you calculate for no, this p of x is going to stay constant. And so what this means is say that your probabilities, so say like your machine, your Naïve based classifier gave this output. So yes, no, right? It gave 0.3, 0.7, right? And remember that all we're trying to do is get the highest probability class variable in our final output. And so what you notice here is that if we multiply or divide all of these by the same constant, given that the constant is positive, the maximum and the minimum stay the same, right? If we multiply this by 5, right, we get 1.5, 3.5. Right? If we divide each of these by 3, we get 0.1 and 0.23, blah, blah, right? And no matter what you multiply, no matter what constant you multiply these two by, this one is always going to be greater. Again, given that the constant is positive. And so, so that means that if they're all multiplied by the same constant, and we're only trying to find the highest, then theoretically we should be able to multiply, or if they're all divided by the same constant, we should be able to cancel out this constant, which again is the same for every single output class. And the highest should still be the same class. And so if we take this out, this is like multiplying, so if we take out this constant, this is the same thing as essentially, so if we take this out of all the formulas, right, this is essentially the same thing as multiplying the yes by this constant, multiplying the no by this constant. All right, and again, the highest is still going to remain the highest regardless, right? If you know this notation, then you can say that Py, given the input feature x, is proportional to this. And but it's fine if you don't know the notation, but just that it's fine to be able to take out the bottom, right? And we're still going to get the highest. We're still going to end up with the same classification, right? The same highest probability. So we have this equation, you know, simplified because you don't need to consider the bottom anymore, the P of x, right? And so now we have this thing. So how do we calculate these two probabilities, right? So let's start with P of y. Well, this one's actually pretty easy because it's literally just the probability of your output or of your output class variable, right? So if you're testing yes, right, P of yes x, right? So P of yes would just be the fraction of all of your entire data set that has a yes label, right? So if your data set, I'm just gonna label yes with like y and n, right? You had these features, and then, you know, good day to golf or not, right? So say there's yes, 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 no, right? So if you're to pick a sample from here at random, if you're to pick a sample from here at random, what is the probability that the label is yes? Well, all you have to do here is just add up the amount of yeses there are here, so that'd be 3, over the total amount of entries you have, which is 4, right? So the probability of yes here, that if you pick a random sample from here, that it would be a good day to go golfing, the probability of this would be 3 over 4, right? And so that's how we calculate the first part, right? P of y. Again, if we're doing this calculation for the no class, again, we just get, 1 out of 4. Right, so that's the probability of that particular class variable. And now how do we get this probability? It looks pretty ugly, but it's actually not that bad. So what you have to do in this case, I'm gonna move this down here. All right, so now what we want to calculate is this. Actually, I'm just gonna delete everything else here. This here. All right, so you're trying to find the probability of xi given y. So let me just make a simple data set here of of our xi and our y, right? So what is a good day to go golfing or not? All right, so again, I'll put yes, 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 no, no. And then for xi, I'll put yes, yes, no, yes, yes, no. Right? So what we're trying to find here is the probability of xi being true, of it being, well, I guess I should have drawn true or false here, but I mean, you could just, yeah, you can infer that. So of xi being true, given, right, the conditional, that y is also true. And so if you're only looking at the cases where y is true, where it is a good day to go golfing, then that means you disregard the cases where y is false. because you're not looking at those, you're not considering those in this conditional probability. So you'd essentially, you just ignore these, right? Cut these off, right? And you'd only look at this, you'd only look at the cases where y is true. And so then you can do the same, you can count them up and divide them again. So out of all the cases where y is yes, where y is true, what's the probability that xi is also true? Well, we have 1, 2, 3. Okay, 1, 2, 3 yeses, and then 1 no. So that'd just be 3/4, right, for this particular data set. And so yeah, that's essentially what you do to be able to find a particular xi of y. You only take into consideration the cases where y is true, and then you take out of those possibilities, you take the ones where xi is also true, and then you divide it by the total amount of cases where y is true, right? And so then you just perform this, and then you do it for every single feature you have, right? So you do it for this one, this one, this one, and this one. You get all of those probabilities, you multiply them together, then you multiply them by the initial, the probability of y in the first place, of yes, right? And so, yeah, then once you have all these probabilities, then it's just a simple matter of, so let me copy this. So now, you have all these possibilities. All you have to do is find the highest. So now we can find that our y is equal to argmax, and this essentially just tells you argmax of y. This essentially just tells you for every value of y, which one is the highest, and it returns the highest value, right? The class with the highest value, right? And then out of all these possibilities, for every single possible y, right? And so, if we were to calculate for golf again, if it was yes like 0.88 and no 0.12, this would return the yes class variable, that y is true, right? And so yeah, that's essentially how naive Bayes works, right? You just find the probabilities for every class, you return the highest one, and then the way you find those probabilities is by using that this naive Bayes formula, right? Where is it? This one here, right? Where you find which one it's proportional to. And so this seems all well and good. Once you accept the fact that it assumes that every single feature is independent and of equal weight, but there is one case to consider, and it actually comes up more often than you might think, especially if you have a smaller data set relative to your features, right? And also, just as a general rule, when I say small data set, I mean like relative to features. So if you have like a 10,000 sample data set with one feature, that'd be pretty good, as opposed to a 10,000 sample data set with 200 features, right? That'd be a pretty bad data set, right? And so if you have a small data set, when you're making this calculation, remember that this, this, let me see, this expression here, I remember that it's equal to p of x1 times x2 times blah, 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 right? Times y, blah, blah, blah. However, what happens if you're getting one of these p of x1 given y's or p of xi given y, right? What if you're finding one of these? So you have y, xi, and you have true, true, false, I like false, 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 right? So let's say you're finding your xi given y. Well, again, remember, out of all of our cases where y is true, cases where y is true, so these ones, how many of them are xi? So that'd be 0/2, right? And so what happens if one of these values is 0? Well, as you may know from like third grade math, anything multiplied by 0 is 0. So this entire expression would go to 0, right? And that would just be naive Bayesian action, right? That's just what the formula is saying. However, the problem with this is that there are other probabilities, right? If you have like 100 features in your data set and only one of them is 0, you're essentially throwing out all the information that you got from the other 99 features. And you know, if you're fine with that, then go ahead. But for most, this can be a problem. Like I said, especially with smaller data sets, right, where you want to keep as much information as possible. So what can we do in this case? Well, now this is where we introduce something called smoothing. All right, this is more of a statistical method, but it works well here. Right? And so how does smoothing work? Well, the way that you calculate, where is it? Yeah, so the way that you do smoothing is that, let me draw another data set one more time. So given, you know, xi, y. This time let's do more than just 2 classes, right? Let's do, you know, the y's like a, b, c, right, as possible classes. B, b, c, a, right? And then xi, you know, xi is like a, right? And so now, say that we're trying to find, so let's say like we're doing, you know, performing all this, and on one of our calculations, we have to find probability of our particular xi happens to be c, probability of c given, and then the class that we're checking for, so our y here, in this case happens to be b, right? So probability of c given b. Well, again, you can see here there's 2 b's here, but there's no c's here, so that'd be 0/2. So what we do whenever we make any one of these probabilities, right, in order to produce smoothing, is that we take our observations, right? So let me actually, let me copy this whole thing over. Right, we take our observations, you know, with our given our given class that we're testing for us, which is B. All right, so I'll take this out. Delete all this, right? So now what we're going to do is we're going to take all these observations, and then we're going to add some. Now what do we add? Well, we're going to add one observation for every single unique class that xi can be, right? So remember that we said xi can be a, b, or c. Y can also be a, b, or c, right? So xi, you can say x is equal to x1, x2, dot, 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 to xd, right? Where d denotes the total number of unique classes that xi can take on, right? And so, oh, sorry, okay, I apologize. This is not the total amount of classes. This is total amount of classes that a particular feature this can take. This is actually the total number of features. All right, my bad. So yeah, D denotes the total number of features we have here. All right, so for xi, what we do here is that we're going to define another variable here called the pseudo count. And we're just going to denote that pseudo count as k. Right? And for this one, we're just going to use k equals 1. Okay? So k equals 1. All right? And so now, what we're going to do is that we're going to pretend that we saw every single outcome k extra times. Right? So what does this mean? Well, well, this just means that we can add more, we just add more observations here that we pretend that we see, right? Remember that we don't actually see these, but with smoothing, this is what we do to, to add everything on and make it, to achieve our final goal, right? So we add a K, and right for here, let's just add A, B, C, right? This is one of every possible, you know, what value this can take. And then Y, again, we're just going to assume it's B, right? So what does this do? Well, now if we take another observation of the probability of C given B, we have that there's one extra C, right, out of these 5 B's. So you get 1 over 5. It's no longer 0. Now, why is this not 0? Well, let's look at the equation for P of C equals B. So I'm going to move this down. All right, so say that this equation is equal to, say, I'm trying to think of like a good variable. So for the bottom, let's say n, right? N for the total number of observations we make. And, ignoring our fake observations here that we just added in, right? Only real observations, we have 2, right? And then this, let's do, I don't know, like, just C, right? Just as an example. So C would represent the total number of observations of xi that are C, right? So actually, let me, this is a function, right? So of xi, how many of them are C? Oh, we can see that there's 0. So C of xi is equal to 0 and is equal to 2, right? Again, we get 0 over 2. However, when we add an observation, or we add k observations, right, for every possible class variable, right? So we add 1 for A, we add 1 for B, we add 1 for C, right? And then again, this is denoted by D. So A, B, C, right? And so if D is the total number of possible values that xi can take on, possible classes, denoted by D, right? We can say that we get k times D extra observations. And you can see why, right? Because if you add, if you observe 3 classes 1 more time, then you get, 3 more observations. If you observe 5 classes 1 extra time, you get 5 extra observations. And if your k is 2, for example, right, then we add 2 more observations for each class. Right, so now ABC, ABC, assuming this is 2, then, you get 3 classes of each observed 2 more times, so 3 times 2 is 6, right? So k times D, right? And remember that for every class that you observe, right, for every possible class you observe, only one of them is going to be the one that you're looking for, right? In this case, we're looking for C. So here, if we observe the D classes, so the 3 classes, k times, k of them are going to be C, the one we're looking for, right? So one of them is C. If we observe it each of these classes twice, we get 2 C's. If we observe each of them 3 times, right, we're going to end up with 3 C's, and so on. And so you can see that for your total observations of C of xi is going to increase by 1, or is going to increase by k whenever you do this. All right, and so this ends up being your formula for finding the final conditional probability. And so whenever you pick, what's it called, your pseudo count value, your k, to be 1, that's called Laplace smoothing. And if you pick it to be, where is it? I don't think we wrote it down. Oh yeah, here. If you pick it to be anything else, then the general version is called Lidstone smoothing, right? And so here we can see the same formula that we had here, right? Where instead of k being our pseudo pseudo count, we have this alpha, right? And x of I denotes which possible class it is. And so yeah, this is just the same formula we had, right? So x of I over n, right? Instead here we had c of x of I plus alpha. We had plus k here, and then plus alpha, blah, 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 right? We had the same thing, right? So now, now that we have this formula down, you can see why it helps you it helps you dodge those errors where you have some classes equal to 0, right? Some of these probabilities equal to 0, and it just ruins the whole thing. Because with k is equal to 1, right, or k is equal to anything other than 0 and is positive, you're going to have at least one observation or more that is of the class that you're getting the probability for, right? Here we have at least one C, right? Because it guarantees, since we search every single class, at least one of them is going to be the one you're looking for, right? And so the last thing, this part's going to be pretty quick, is Gaussian Naïve Bayes. And so how do you choose the K? So K is essentially just it's like a hyperparameter that you choose when you're performing your Naïve Bayes, and it's just a trade-off that you have to sort of fine-tune yourself. So essentially, it's like smoothing your input, right? So if you're like if I were to search up like graph smoothing, let me see, right? This is like not representative of what's actually happening, but it's sort of visualization, right? Where you have this data and it's sort of smoothing out, right? And like you see here, you lose some of the detail, right here. You lose some of the detail, but you avoid that error where it's not necessarily an error, but you avoid the case where everything is just 0, right? And again, the more smoothing you do, right, the higher your pseudo count, the higher your k value, the more data you're gonna lose, right? Because if you go, right, if you see here, the more k that you choose, your real observations here, right? We only had 2 real observations. If you have a lot of fake observations, right, your final probability is not going to be like actually representative, because the real observations here are just going to be drowned out, right? They're going to be overwhelmed by the amount of pretend observations you make with a high k value, right? So it's just a matter of fine tuning of what you think is going to yield you the most accurate results, with still good results that are non-zero. Right, so the last thing is just Gaussian distribution. And so what we've been doing is something called multinomial Naïve Bayes, right, where we just work with multiple classes, right, with A, B, and C. And with what's it called? With what we were doing earlier in particular, where we had a binary yes or no, right? And binary yes or no inputs. So in the case that you have a binary yes or no input variable or vector, right, x of I, you can actually use something called Bernoulli Naïve Bayes. And essentially what these different methods of Naïve Bayes do is that they allow you to use different formulas for finding the conditional probabilities here, for finding all of these, right? Because you're finding like a lot of these whenever you do Naïve Bayes, right? And so if you make it so that all of your input features, every single one of your input features is a binary class, yes or no, true or false, then you can actually use, instead of having to add them up and then divide it by however many there are, and then doing that n times and multiplying them all together, blah, blah, blah. And instead of doing all of that, you can just replace it with this equation, right? And again, this is assuming that you have binary classes for your inputs, right? And this, again, this just assumes a Bernoulli distribution, where if you have like 0.4 chance, one case is 0.4, then given that it's binomial, then the other, given that it's binary, then the other case must be like 0.6. All right, and that's what we're doing here. 1 minus pki, blah, blah, blah. Right? And so that's just a way to find, that's a way to do it with binomial inputs. And Gaussian distribution is actually a way to be able to use naive Bayes on not just class inputs, right, classification inputs with discrete classes, but also continuous and numerical inputs, right? And this is based on something called the Gaussian distribution or the normal distribution that you've probably seen here, also known as like the bell curve or standard deviation, right? And this is essentially a formula for finding given a value, how likely is it to deviate from the center, right? This is shows a distribution of a particular value for a population. And so this is a formula for Gaussian distribution. And I know it seems pretty complicated, but essentially all this is doing is just replacing this process of, you want to find P probability of C given B. Just take all the B's, find all the C's. It's 0, 0 over 2, and that's your final answer, right? It's just replacing that process of adding them, dividing, counting, with a simple formula here. Simple, I say, but I mean, this is pretty simple for a computer at least, right? Where rho is the standard deviation, right? And so this is actually how you can integrate not just classification, discrete inputs into your naive Bayes, but also regression. And you can even mix and match because remember, this is only finding for a particular probability, right? And so while you're calculating this, you can just choose, is this a classification, is this like a discrete input? If it is, then just add and divide, find the probability. If it's a regression input, then do this calculation. Right? And that's how you can actually perform naive Bayes on more than just classification inputs or discrete inputs. I think that's all we have for classification for now for like teaching. Now we're just going to go into the implementation. Is there anything you think I missed, Kaushik?
No, I think there's actually more that you taught than there is in the actual code. So we're going to be missing a bit of stuff in terms of smoothness. But I think you covered almost everything. Yeah.
Okay.
Cool. Here.
I'm gonna let you screen share.
Yeah. This is the code, and I should probably start with those slides over there too. So this specific example is going to go over classifying flower species. Can you see the screen? It's a
Yeah.
What do you see right now? Is it like a presentation?
No, it's just like the window.
Oh,
it's not present. Okay, now it's in present mode.
Cool. All right. So yeah, and so there's 4 features that we're using: the sepal length, sepal width, petal length, petal width. I have no idea like this is an image, but I don't know. They're just numbers. It's not discrete data. It's actual number data. So continuous data. So we're going to be splitting the flowers in our data set into 3 separate classes. These 3, I believe, and so it'll follow the process of naive Bayes that Henry's been describing. And because we're using continuous data, in order to calculate that probability, right, it'll actually be using the Gaussian naive Bayes formula. And at the end, it'll predict the final probability for each class and assigns the highest one to whichever prediction or whatever data you're giving it to predict with. So let's go over the code real quick. This is just a couple of functions to import from different libraries. Load CSV. This is a function that's made purely just to import the data set and to kind of show you all how the data set looks. It's basically got these 5 columns where the last one is the actual class that this flower is, and these are kind of the 4 features that I talked about in the presentation. And so once we read in all of those into a with this like CSV reader, we're able to just return that. All of these functions will be called at the end. They're just being defined up here first. This function right here, the column to float, that will take the, because we're reading them in with the CSV reader, it automatically assumes they're strings first. You have to actually like assign them to floats and integers. That's what these two functions do. And separate by class, this separates the data set into a dictionary with three separate, because there's three classes, right? So it'll have three separate entries, and within each entry you'll have basically like a list of all the rows. So, and like a multi-dimensional array there. And then once you or actually I'll go over the process later once we go through everything, but then these two other functions right here, the mean and the standard deviation, those are pretty self-explanatory. You know, if you'd have the mean, you just take the sum of the numbers and you divide by how many numbers you have, and then standard deviation, you just use the standard deviation formula, which is pretty simple for a computer to do. And these functions right here, these are the ones that will actually give you the summaries for the data. So these are going to be making these, what's it called, the calculations, and providing you with the probabilities for each class based off of the values that you input into the function. So starting with this this is the predict function. And so basically what you're going to do is at the bottom, this is what's actually starting everything. So you start by calling this predict function, right? And within the predict function, the first thing you want to do is calculate the class probabilities. You want to call that function. And so within that function, what you're doing here is you're getting the total number of rows, then getting the what's it called? Making a dictionary, and then after that, you're basically going to be looping through the all of the values and the summaries from the summaries.items. And so let's see. So this predict function, as you can see, oh, actually, no, I skipped ahead. My bad. So it starts with this model right here, right? So the first thing we're doing is getting the data, we're loading it up, and then within each of those, within that, we're going to convert all of the floats to the strings to floats, and then the what's it called? The other strings to integers, depending on which ones have to be converted to what. And so once we call those two functions from earlier, if you'll remember up here, we'll basically have like properly set up the data set, and what's it called? After that, you can start, like, I guess, quote unquote training. It's more just like summarizing is what it's called here. And so this summarize by class function, that is actually going to like give you the probabilities. It's going to do all those calculations for each basically row inside of this data. So inside of the data set. So within the model, right? If you go to summarize by class, the first thing you're doing is separating all of the inputs in the data set into distinct like entries in a dictionary, or yeah, and that's separated. If you remember, separate by class was a function up here where we made a dictionary and we went through and we basically took all of the class values as kind of like the key for the dictionary, and then the value of that was going to be like a list of all the rows with that class value. And so once that was done, right, we made a summaries dictionary here. And so that summaries dictionary, it basically takes this function right here, the output of this function, summarize data set. And if y'all can see up here, it basically calculates using those three functions, the mean, the standard deviation, and then the, well, just the length, I guess, of how many entries there are for that column. And it'll, and in this case, you know, since we're actually doing it for the entire data set, where were we? Because we're doing it for the entire data set, or sorry, for each class value within that data set, basically the rows that are being passed are specific to a certain class value. And so this is kind of like 2 dimensions, if you can see here. And it's so the class value, for each class value, it's going to basically pass all the rows that are associated with that class value as we got from our separated list, or sorry, dictionary. And so once it returns the summaries of all of this, the mean, the standard deviation, and the length of each one, it'll basically return the summaries back to where we first called it, which what's it called? Is basically saved within the model, right? Why do I feel like I'm skipping a step? Hmm. All right, 1 second. Because we didn't actually use the. Okay, that makes sense. All right, so after we do that, then we're gonna go through and figure out what the label is for a certain input, which has these 4 values for the 4 inputs. I don't remember the exact names. It was those 4 features of a flower. And so you want to actually call this predict function. And so this model basically, right, supposedly has all this data summarized for each of the classes. And so now that you have the mean, the standard deviation, and that number of entries for each of the classes, now you're able to actually make a prediction. And so within this prediction, we're going to pass it the summaries, as defined earlier, that model. And then we're going to pass it the specific row that we're trying to find a prediction of. And so the first thing you want to do is calculate the probabilities for each, well, you can call this function with by passing it the summaries in that specific row. And so what that'll do is for this, for every single class, it'll calculate the probability that that class is the correct one. And so it'll get this, first thing it's doing here is figuring out the total number of rows here. Then you're making that dictionary, right? And I think we did go a little bit over this function earlier. So once we have made this dictionary, whatever, and then we have the value and the class summaries from the summaries items, like summaries.items, that should just return the values, I believe. And so what we do from there is the probabilities dictionary is within that, it's basically being assigned for that class value. You're going to give it the summaries of 0 and 2. So if you remember the summaries function, or sorry, the summaries dictionary, I guess, or array list right there, has these 3 things assigned in those 3 columns, 0, 1, and 2. And so we have the mean and the length. And so you're basically multiplying the mean and the length of that, and then dividing it by the total number of rows. So in this case, we're actually keeping that constant from what Henry mentioned earlier. And so after that, what are we doing? So we are taking the length of the number of summaries we have. And so we're basically going to loop through that. And for each of those, we're going to get the mean and then the standard deviation. And this is just going to be wasted. But what we're going to do with that, because we don't actually have the probability, right? Because this is just simply the mean and standard deviation of those 2 values for our specific class. We need to actually calculate the probability by using our input of row, right? And so this is where that Gaussian probability, normalization function or whatever, comes into play. And that's this function right here. It's that somewhat complex looking equation that Henry showed on the presentation. You're basically going to pass it the mean, the standard deviation, and then the actual value. And based off of the distribution, it'll return a value for the probability. And so what you're going to do afterwards is basically it'll return all of the probabilities to this prediction right here. And so then you have the best label, best probability just being initialized here. And essentially what you're doing is you're finding the maximum here. And once you get the maximum probability, that's the value of the class that is associated with that probability is going to be the label of your input. And so you're just printing it out here. And if you, as you can see here, this with this input, it ended up predicting that it was this class of flower. That was super confusing, but yeah.
One, are you done?
Yeah, I'm good.
Yeah, one last thing. With if you remember the Bernoulli Naïve Bayes classification, that applies specifically where when all of your input input vector x is composed of entirely binomial classes. That in particular is has been utilized and can be utilized in NLP, natural language processing, in which all you do is literally just indicate whether or not like a word exists in a document, right? Where like, bank, yes or no, river, yes or no, man, yes or no. You can indicate whether a word exists or not in a document, and it performs surprisingly well. For spam filtering tasks, for document classification tasks, stuff like that. And even though it may not be up to par with what exists today for those kinds of tasks, it still was one of like the original methods for doing that performed surprisingly well, given how simple and seemingly dumb the algorithm seems. But yes, I think we're done for today if we've finished through all the code and stuff. Let's see. Any more questions or clarifications?